Okay, so let's try to look at what is called the Lagrange multipliers. So overall, what we are still trying to do is that we are still trying to find convenient methods of determining the local minimas as well as the local maximas of a given function. So in the previous tutorial, of course, I've shared the link in the description. Um, we were using the second partial test to determine the, like, of course you have to determine the discriminant, so on and so forth, and we try to see if you have relative minima, relative maxima, as well as maybe you have saddle points or something. But now we want to try to take a different approach, and in this case we call that Lagrange multiplier. So this is just more like a method. So what it is that the Lagrange multiplier is just a method used for finding local maxima and minima of a function that is subject to a constraint. So it's like you have a function f, okay? Let me say f, you want to determine the local maxima and minima of this function that is subject to a constraint that I'm going to name as my g. Okay, so in this case, let's say this is your x comma y comma z. That's our function that is subject to what? To this constraint that is g comma, that is g, which is x comma y comma z there. Okay, so now the thing is that before I go any further, like when it comes to a constraint, okay, when it comes to a constraint is nothing but like it's a restriction in simple terms. Okay, it's a restriction, and we'll see this when we try to, we'll graph one of the questions that we're going to go through, so that we really see where what we mean when talking about a constraint being a restriction. Okay, so a function whose local minima and maxima you're trying to determine can have a single constraint. In this case I have my g, or it can have multiple constraints. Okay, so if you have multiple constraints in this case, let me say you have two constraints, such as I'll use h in this case. That is going to be your h, you have your x comma y comma z. So how we deal with this is this way. So the constraints that we have, okay, uh, the maxima constraints, okay, I'll say maxima constraints, as well as the minima constraints. These are found from the intersection. Okay, those are found from those are found from the intersection. So one thing that we have to understand is that here, when it comes to the normals of level curves, normals of level curves are scalar multiples of each other. That's one thing that we have to understand. So let's say here we have the normal for this function, that whose local minimum and maximum we are looking for. The normal of that one is more like you're finding the gradient. That would be that. Then you have your x comma y comma z. Okay, that is going to be equals to if you determine the normal for that one, and we say the normal of level curves are scalar multiples of each other, you're going to multiply by a constant. Let me say you're multiplying by a constant k. Okay, then you have the normal of that function, which is your g x comma y comma what comma z. All right, so this is when you have a function f whose constraint is that one that you're given. It's like you're given one constraint. Okay, so if it's let's say if you're given two constraints including the h here, you're going to say that to be your plus, let me name this as what letter can I use here? Let me use d. Okay, let me use d there, multiply by that one there. Then you have your h comma y comma your x y comma z, like that. So here what it is that these multipliers that we have here, these are the ones that we are calling the Lagrange multipliers. And for the k, we normally use lambda. Okay, I believe we are familiar with this one. Okay, then for the part for d, we use mu. Okay, so this is what we use. So it could be any other letter or anything, but any other symbol, but these are the ones that we use. These are I would call them the universal ones that we use. So the questions that you're going to look at, like from the, just when you read the question, it will be very easy for you to tell whether you have two constraints or you have a single constraint. And it's very important that you understand when is it that when you have a single constraint, when is it that when you have two constraints. Okay, because if you only get a function, then you determine the local minima as well as the local maxima, or maybe you're just finding one, you're not finding the other, you leave out the other constraint, you are not going to get something that is correct. Okay, so something else that we also have to understand is that the gradient gives the normal to the level curve. So that's why I'm writing it like this. Like, this is what we use to find the gradient. That's why if I have a function of two variables, let's say I have my f x comma y. Okay, for me, let's say I want to determine the gradient of that. Okay, the actual value of the gradient. This I'm just going to say, I'm going to say it will be my f x comma y, which is going to be equals to, let's say um, I get n in the I plus m in the what, m in the j. Okay, so this is going to give me the actual value of the gradient. What do I mean? We know that gradient, which I will denote using, let me say g, is equals to what, the rise over the what, over the run. In this case, our rise is what, is our m, and our run is equals to what, is our n. So this, just by doing this, it's more like what we have been doing every time by when you're determining the gradient. Yeah, but in this case, you're also applying it when it comes to functions of three variables. Okay, so I believe anything else maybe that I've not talked about, we'll try to bring it up when you start solving the questions that we have. So we have multiple questions that we are going to go through. One of the questions is a question that we did in the previous video, and I recommend you go through that one. It's actually this question. Okay, is this question when I say a rectangular box without a lid is to be made from uh, 12 meter cubic of cardboard. Find the maximum volume of such a box. So here it's more like you are maximizing. And remember to say the volume that we found was what? Was I said 4 units squared, but units cubic, I mean. But of course, the volume, we are the unit that we are given for the area there is meter, so it's going to be 4 meters cubic. But you're able to substitute there the units. I believe you know that I meant the meters cubic. Okay, so meaning the answer that we should expect for this one, it should be a 4. So it's just that the question specified that we need to use LaGrange, okay, LaGrange multipliers, but there it was more like the question just open. It's up to you. If the question is just open, it's up to you to choose which method you want to use. If you have enough time, you can use both methods just to confirm. So we should expect 4 meter cubic there. Okay, so let's begin with this question. We are saying find the extreme value of the function f of xy is equals to x squared plus 2y squared on the circle um, x squared plus y squared is equals to 1. So what it is here is that the function that we have, our f of x comma y is equals to what, is equals to x squared plus 2y squared. So now the constraint that we have, I'm going to name it as my g x comma what, x comma y is equals to what, x squared plus y squared. I don't need to include this one here, okay, because even if like when I'm differentiating, that will still be a 0, hence I don't need it. Okay, so now what it is here is that first things first, find the normal vector. So here it's like the gradient, so that will be x comma y. So differentiate this with respect to x and y at the same time. So this is going to give us, if you differentiate with respect to x, you're going to have 2x in the I. Wait a minute. Okay, 2x in the I, that will be plus 4y in the what, in the j. Then what about the other one? Okay, our constraint there, this is going to be 2x in the I, okay, plus 2y in the j, like that. All right, so here now, since I only have one constraint, it's just a matter of me saying, okay, I'm saying my normal vector for that function, okay, that will be equals to lambda, okay, multiplied by my constraint, which is my uh, the derivative, or let me say the normal vector for my constraint. So the normal vector for my function, whose local minima and maximum I'm looking for, I'm going to say is 2x in the I plus 4y in the j, like that, is equals to lambda, okay, multiplied by that, meaning I'm multiplying by what I have here. That is going to be 2x in the I plus lambda by 2y in the what, in the j. So now it's just a matter of equating this part, you equate with that part, this one you equate it with this one. What are we going to get? So I'm going to say it's 2x. Of course, when you equate this one with that one, I don't need to consider the I. Even if I do, they're going to cancel out each other. So that would be like lambda, then I have 2x there. So what does this mean? My lambda is nothing but equals to what? Equals to 1. Alright? Let me try to determine what the other one is. Meaning, I'm talking about this part where I have 4y in the j, which I'll equate with what? With what I have there, which would be lambda. Then I have 2y like that. Okay, so now I want to try to determine what my y is. Okay, I want to try to determine what my y is. So I'll say, okay, my y will be equals to my lambda. I found what? I found 1. So that'd be like I have 2y like that. So this, you're going to find that your y is equals to 0. What makes y to be equals to 0 here? Okay, so the thing is that if you say 4y minus 2y is equals to 0, you factor out the y, you have your y minus what? I mean your 4 minus the 2 there. Okay, maybe not even doing that. This is like 4y minus 2y. That will give us 2y is equals to what? Is equals to 0, making your y to be equals to what? To be equals to 0, because you're going to say your y is equals to 0 divided by what? 2, giving you what? A 0 there. Okay, so after substituting the lambda that we have, which is our 1, in that in this equation, we found that our y is equals to what? Our y is equals to 0. So remember, what we are trying to look for here are the what? Are the critical points. Okay, what you're trying to look for are the critical points. So how then do I come up with my value of x when my values of x when y is equals to 0? I'll come and say, okay, uh, this is going to be this way. uh, I'll get this equation that I have, which is this one here. So I'll say I have my x squared plus y squared is equals to 1. So my on y here, y is equals to 0. So that would be like your x squared is equals to what? Is equals to 1. So meaning your x is equals to positive or negative what? Positive or negative 1. Okay, so we have determined that when our y is equals to 0, okay, when our y is equals to 0, our x is positive or negative what? Negative 1, like that. Those are one of the what? The critical points that we have. So far I have two critical points. I have 1 comma 0 and I have negative 1 comma what? Comma 0. Let me try to find the other one. Let me try to find the other one. So now I've also determined that, having determined that your lambda is equals to what? Your lambda is equals to 1. If we substitute in this same equation that we have, you're going to find that your x is equals to what? Your x is equals to 0. Okay, we are going to determine that our x is equals to 0. Wait, are we going to get the same thing if I do it the other way around? Let me try. If I say 4y is equals to lambda 2y like that, meaning when I divide both sides by 2y, that goes, I'm going to get I'm going to get a 2, meaning lambda is equals to 2. So now if I come here, I substitute. Let me see if I'm going to get something cool. So okay, yeah, if we say 2x is equals to, my lambda is a 2, so it's a 2 multiplied by 2x, we get 2x will be equals to 4 what? 4x. You bring it the other side, like that, to be like your 2x minus 4x is equals to what? Is equals to 0, of which your x is going to be what? Is going to be equals to 0. Okay, yeah, so that is equals to 0. So now we get this equation again. We want to determine what our y is when x is equals to 0. So that would be like 0 squared plus y squared is equals to what? Is equals to 1. I don't need to put this 0 anyways. So my y is nothing but positive or negative what? Positive or negative 1. That's what I've determined. So meaning when my x is 0, okay, my y is positive or negative what? Positive or negative 1. So these are the 4 critical points that I have. Okay, so those are the 4 critical points that I have. So now I have the points, I have 0 comma 1, I have 0 comma negative 1. Okay, I also have 1 comma 0, I have negative 1 comma what comma 0. So now for me to determine the maxima as well as the minima, I need to use this function that I have there. So that would be like my f at 0 comma 1. What am I going to get? If I put 0 squared here, then I'll say plus 2 1 squared. What are we going to get? We get we are going to get a 2. That is when I use this one here. Now let's try to use the other one. So if we say f 0 comma negative 1, we're going to say it is 0 squared plus 2 negative 1 squared. You're still going to get a what? A 2. So now let's say if we say f 1 comma 0, what are we going to get? That would be like a 1 squared plus a 2 by 0 squared, giving us a what? Giving us a 1. If we say f negative 1 comma 0, what are we going to get? You're going to get negative 1 squared plus, okay, plus 2. You see you have a 0 squared here, which gives you what? Which gives you a 0. So what you observe is that when on the critical points that are what? 0 comma positive or negative 1, what we get is the value that we get is a what? Is a 2, which I'm going to say this is our what? That's our max. Okay, then when you have the points positive or negative 1 comma 0, we get what? We get a 1. Okay, and this is our what? That's our mean. Hence we have determined. So the key thing, determine the critical points. From those critical points, the values of x and the values of y that you determine, take those values and substitute in the equation whose local minima and maxima you are looking for. Don't substitute in the constraint, because you're looking for the local minimas and maximas of the function, which is this one here. So if we're to substitute in this one, then it's obvious we have not really understood what the theory of LaGrange is talking about, or perhaps how to deal with um, local minimas as well as maximas. Okay, so now let's try to look at another example. So our second example is in this way. We are saying find the points on the sphere x squared plus y squared plus z squared is equals to 4 that are closest to and furthest from the point 3 comma 1 comma negative 1. So first thing first, this what I have here, my what I have at this point, this is my constraint. Okay, that's a constraint that I have. So how is it going to be? So I'm going to name this as my g, then x comma y comma z, which is going to be equals to x squared plus y squared plus z squared. I don't need to include the 4. Okay, I'll say z squared like that. So now how is this going to be? So my function f that I'm looking for, I'm going to get it from this. And since you're talking about, like, it's more like you're talking about a point, a sphere, like that's a surface. That's we have the sphere and a point. So how we are going to relate this is that for us to get the equation of the function that whose locus we are looking for, we're going to get it from this, and that is simply the distance. You know that distance is equal to the square root of x minus x initial squared plus y minus y initial squared plus z minus z initial squared, like that. Okay, but I'm going to use it in this way. I'm just going to say it will be my f of x comma y comma z, which is going to be equals to everything that's inside without the root there. Okay, so that would be my x minus x initial squared plus y minus y initial squared plus z minus z initial squared. Okay, how is this going to be now? This is going to be like my f x comma y comma z will be equals to my x minus, what is my x initial? It's a 3, so squared. I'm getting from those points there. Okay, so plus I have my y minus 1 squared plus I'll have my z plus 1 squared. Why is it a plus? Is we have a minus here and our z is a negative. Z initial is a -1, so it becomes a positive. So once again, we only have one constraint, hence we just now need to determine the what, the the vector equation. So for my constraint, which is my g x comma y comma z, that will be equals to 2x in the I plus 2y in the j plus 2z in the k. Okay, so what about this one here? uh, we're going to fit here. So the vector, oh, why not I just write it this side? So our vector of the function whose locals we are looking for, f x comma y comma z, is equals to, differentiate this part with respect to x, or let me just say, I believe we know what we do by now. So that would be x minus 3, okay, that's in the I, plus we are going to get 2 y minus 1 in the j, okay, then plus we have our 2 z minus, or z plus 1 I mean, in the k, like that. Okay, so I'm going to erase this part for now, but if I need it I'll have to bring it back, but I'll erase it for now. So remember, we are equating this one to this one multiplied by the lambda, which is our multiplier. So meaning this one we equate to this one, but we are multiplying by the lambda. So what you're going to say is you're going to say it is your 2 x minus 3 equating what, lambda 2x, like that. Okay, that's how they are related. What about the other one? Okay, for this part we are going to say it is a 2y minus 1 equals to what, lambda 2y. The last one we have our 2z plus 1, which is equals to our 2, wait, I forgot, this is supposed to be lambda, what do we have? We have 2z, like that. Okay, that's what we need for now. So now it's just now the matter of determining what your lambda is. So that's the key. Your lambda is more like a constant, and that's the one that we are looking for. Then it will help us to find the values of x and y and z. Then we just have to substitute in this one, then we determine what it is at the end. So in this case, of course we know that we can divide all the sides by, how is this going to be? We can erase the 2 there, the 2 goes, I believe you know where this is going. That's those 2 goes. It's like you're just dividing both sides by 2 for all of them, and that's what you're going to have. Okay, so how is now this one going to be? So what it is that this side I have my x minus 3 is equals to lambda x. So I'm going to say x minus lambda x here is equals to what? Is equals to negative, wait, it's going to be positive 3. Okay, it's going to be positive 3. So I'm going to factor out the x. My x will be x 1 minus lambda is equals to 3. So my x will be equals to what? Will be equals to 3 over what? 3 over 1 minus lambda, like that. So if you do the same for this one and for this one, you end up with your y, okay, your y being equals to 1 over 1 minus lambda. Then your z will be equals to, your z is going to be equals to minus 1 over 1 minus what? 1 minus lambda, like that. Okay, so we need to keep this in mind, they are very important. We will need to use them to determine what our lambda is. So meaning we are saying our x is equals to 3 over 1 minus lambda there. Okay, then our y is equals to 1 over 1 minus lambda. Then what about our z? So we have determined that our z is equals to minus 1 over 1 minus the lambda, like that. So um, how then do we determine what the value for lambda is? Okay, how do we determine what our value for lambda is? So you need to pick this equation, which is our constraint, and that will help us determine what our lambda is. So meaning you are going to say, where there's x, you are going to put 3 over what, 1 minus lambda, then we say squared. Okay, in fact let me not waste time. When we square that, that is going to give us a what, a 9 over what, 1 minus lambda squared, plus you square that, you're going to get a 1 over 1 minus lambda squared, like that. Then the other part, you find that this is going to be a positive, because when I square -1, I'm going to get positive, so that would be 1 over uh, 1 minus lambda squared, and we say this is nothing but equals to what, equals to 4, this 4 that I have right here. So now we can make this a single fraction. That is going to give us 11, because 9 plus this one plus that one, that's give us 11, because the denominator is the same. So I have 1 minus lambda squared is equals to what, is equals to 4. So remember, we are trying to determine what our lambda is. So my 1 minus lambda squared is equals to 11 over what, over 4. Okay, that's going to be 11 over 4. So what I need to do now is that I need to square both sides. Okay, I'm looking for the lambda, remember. So that's going to be, that will be equals to positive or negative the square root of 11 divided by what, divided by 2. Why am I saying 2? Because when you say the square root of 4, that will give you a 2, like that. Okay, so now at least that's what I have for now. So I'm going to say 1 minus lambda is equals to what, positive or negative square root of 11 divided by what, divided by 2. But now this is what is going to help me to determine the what, the values of x and the values of y. But if you observe, I don't really need to like I don't really need to like substitute as much for me to come up with for me to, I don't need to find the actual value of the lambda, because I know that my x is equals to my x is equals to what is that going to be? It's going to be 3 over 1 minus, what's my lambda, is what I have here. Okay, that's what we have there. So this part here, I can substitute with what, I can substitute with what I have. Okay, so instead of finding the actual value of lambda, just this part, because it's 1 minus lambda, and here I have 1 minus what, 1 minus lambda, I can just say divide by positive or negative root 11 divided by what, divided by 2, of which this just gives me what, positive or negative 6 over what, 6 over square root of 11. Okay, is that correct there? Yeah, I think so. So that's what we have as our x. Very important, we say our x is equals to positive or negative 11 6 over square root of 11. Let's try to determine what our y is. So we say our y will be equals to, so now even our y as well, we just say 1 over, where we have our 1 plus 1 minus lambda there, and we found that our 1 minus lambda is equals to what, we found that that is equals to, wait, why did I erase that one? Okay, but anyway, the value that we got for the lambda was positive or negative square root of 11 divided by what, divided by 2. I'll try not to erase that one. So we'll substitute here and say positive or negative root square root of 11 divided by 2, of which that's just positive or negative 2 over square root of what, 11. So we come to the z. The z is going to be equals to the z is going to be equals to what are we going to do now? So for the z, we are supposed to say minus 1 over positive or negative, that divided by 2. So you observe to say, if I multiply this negative, I mean that positive by that negative, I'm going to get a negative. Okay, then this negative by that negative, I'm going to get what? Positive. So that would be like a 2 over what? 2 over 11. So it's like negative or positive instead of saying positive or negative. So we really need to be careful at that point. So now that we have because what we are looking for is just a point, so no need of really substituting in this or something. Like we don't need to, we are just using those points to come up with a what, to come up with an equation. So now the points that I have for x, the highest value of I mean the, here here how the coordinates are. Let me say for example I say p1 is going to be, when I pick for x, is going to be 6 divided by square root of 11, comma, for the y to be 2 divided by the square root of 11, comma, the z is going to be negative 2 over the square root of 11. Then for p2, okay, that would be your minus 6 divided by the square root of 11, comma, minus 2 over the square root of 11. That would be plus, not just plus, but I'll just say comma, it's positive of course, 2 over the square root of 11. So these are the points that we have. So now the thing is that this point here, okay, this point here is the mean, okay, is the minimum, okay, is, that's the minimum that we have, is the closest. So I'll say that's the point that is closest. Then this point is the what, is the max, that is the what, that is the furthest. And that's how we answer that one. Okay, so what about the, let's try to look at another question. um, let's say we say a rectangular box without a lid is to be made from a 12 meter cubic of cardboard. Find the maximum volume of such a box. How do we do that one? So of course in the previous video we looked at determining that one using the second partial test. Now we're going to try to use the LaGrange multipliers to try to come up with the volume. But of course we have to determine which one is our constraint and which one is our function. So our function in this case, our is, I'll say v of x comma y comma z is equals to what, is equals to x comma y comma z. So now what about our constraint? Our constraint is just we are just going to get it from the what, we're just going to get it from the area. So now for the area, we know that even in the previous video we talked about the area being your xy, okay, plus your 2xz plus your what, your 2yz, and we say that is equals to what, the 12 that we have. So that is going to give us our constraint. So this is going to be, we say our g, okay, our g of x comma y comma z will be equals to xy, okay, that will be your xy plus 2xz plus what, your 2yz, like that. So now here is just a matter of now determining the normal vectors. For that one, the v, that will be your x comma y comma z is equals to what, when you differentiate that with respect to x, y and z, you're going to end up with when you differentiate with respect to x, you're going to have your yz, okay, in the I, plus differentiate with respect to y, you're going to have your xz in the j, plus differentiate with respect to z, that's going to be your xy in the k, like that. So the normal vector for our constraint is going to be that so that is going to be equals to, differentiate that with respect to x, y and z, this what you have here. What you're going to end up with, if you really take it step by step, I'll not do that, I believe you can do that, that will be y plus 2z, okay, in the I, plus your x plus 2z in the j, then that will be plus 2x plus 2y, 2y in the what, in the k, like that. Okay, so now when you try to compare these, equate this to this, what you're going to do is that, of course, you are going to be multiplying by what, the lambda in this case, which is more like our multiplier. So you're going to have your y z to be equals to what, lambda by y plus what, 2z. Then the second part, you're going to have your xz, which is what you have here, equated to this one, but multiplied by the lambda there, so it'll be lambda x plus what, 2z, like that. Then for this part, you're going to have your xy is equals to your lambda by your 2x plus what, your 2y, like that. So how then do we come up with what our lambda is? Because I'm trying to determine what my x and what my y is for this one. Okay, so how do we come up with this one? So what I'm going to do is that I'm going to do some manipulation here. Okay, I'll write it this way. I'm going to multiply this one by what, by x. I'm going to multiply this one by y. I'm going to multiply this one by what, by z. So what it is that I'm going to get xyz. Okay, xyz is equals to what, lambda x, then I have y plus your 2z, like that. Then multiply that by y, that will be your xyz equals to lambda by y, so that will be your x plus your 2z. Okay, then multiply that by z, that is going to be xyz is equals to lambda by z. Then I have 2x plus 2y. That's what I have, like that. So now what you observe is that what I have here, everything, these are equals to each other. Okay, so now I can name this as my equation what, name that as my equation 1. I can name this as my equation what, equation 2. Then we can name this as our equation 3. Okay, so now here, first thing, what you're going to do is that we need to determine what our x is and what our y is. So I'll just try to show you briefly how you determine. I'll show you exactly what your value of y and what your value of x is. So what you're going to do here is that since this and this and this are the same, I'll first of all say, okay, I'm going to equate I'll say equation 2, I equate it with equation what, equation 3. Okay, so when you equate equation 2 to equation 3, meaning when you equate this one, no, not that one, this one with this one, what you're going to end up with is that your y is going to be equals to what, 2z. Okay, that's what you have, comma. When you equate equation 1 to equation 3, what you're going to end up with is that it's going to say your x is equals to what, is equals to y, comma. So when you equate equation no, that's not going to be x equals to that. So our x will be equals to 2z. But if you equate equation 1 to equation 2, that's when you're going to say your x is what, your x is equals to what, your x is equals to y. So that is a very important piece of information, very, very important. Okay, that's going to help us to determine the what, determine the value of what, the value of z. Then that value of z will in turn help us to find the value of what, the value of x as well as the value of y. Okay, so I guess I no longer need up to here, so I'll have to get rid of this. So now to determine my value of z, I'm going to use this from this equation, that equation that you have there. So meaning where there's x, I'm going to say, okay, my x, I'm going to replace with what, with 2z. I'm multiplying by what, the y. And what is my y? It is also what, it's also 2z. Okay, something like that. Then plus your 2, your x is your 2z, 2z by 2z for the y, plus 2, how is that going to be? No, oh no, here I'm supposed to multiply by z. Okay, then plus 2, I have 2z multiplied by what, the z equals to what, equals to 12. So when we do the when you perform some algebra there, so what's going to happen is that your z, you're going to have your z squared, which will be equals to 1. So meaning your z is equals to what? Positive or negative 1. So that z is going to help us to come up with the value of x and the value of y. And where do I get them? I'll get them from this one and that one. So I'll say, okay, my y is going to be equals to. So I'm going to be trying out for positive z, meaning positive 1, my y is going to be equals to 2. For negative, my y is going to be negative 2, so that'll be positive or negative like that. So what about my x? Your x is going to be the same as well, positive or negative 2. Okay, that's what we need. So now, remember to say we are looking for the maximum volume. So you observe to say you have the coordinates positive or negative 2 comma positive or negative 2 comma positive or negative 1 for the z. So the maximum points are the what? 2 comma 2 comma what? Comma 1. So these are the ones that are going to help us determine the what? The volume. And this puts a smile on my face because I know where I'm heading to. It's your x comma y comma z. That's your volume. So your x is your 2, your y is a 2, your z is a what? Is a 1, giving us what? 4 cubic meters as a what? As a volume, which is the same value that we calculated when you're using the what? The second partial test. Okay, so that's how you go about that question. Let's try to look at the last question in this tutorial, which is a D. Okay, so this might be a little involving, but not really involving. So the thing is that first things first, you have two constraints. You have that function, then you have two constraints. You have a plane and you have a cylinder. Okay, so what I'd want us to do is that I'd want us to have a picture of this. Okay, so now these constraints, this one and this one, like they have some kind of like they have a relationship between them, which is like the relationship between a cylinder and a sphere, where they are intersecting each other. That the equation of what you're going to get of that figure, whatever it looks like, that is more like, that is our constraint. If you want to just to use one constraint, but I'll not use one constraint, I'll use two of them. Since I've been using one constraint throughout, it's better I use two constraints now, so that at least we are familiar with how to go about them. So first of all, I would want to graph this so that I give you a picture of how this looks like. I mean, graphing these two so that I show you how it's going to look like. So now here I have my plane with an equation x minus y. Okay, then we have plus z. Okay, plus z equals to 1. This is a plane that we have. Okay, that's a plane that we have right there. Okay, that's a plane that we have. Let's try to put the equation for the cylinder, which is our x squared. Okay, say plus y squared, that will be equals to, we say it's equals to what? It's equals to 1. That's the way it's given. So now you have seen, say, this where the cylinder and the plane are intersecting each other. We have more like, when you look at it from the top, something like that. Let me try to draw something. So it's like we have this elliptic figure kind of thing like that. So that is more like our constraint. So it's more like you are equating the plane equals to what? Equals to that sphere there. Okay, that is what that's what I mean by, like, when you equate them, you use that constraint. Try it out. You see if we are going to get the same thing. So now what I know is that my my function f, then I have my x comma y comma z is equals to what? My x plus 2y plus 3z. Okay, then my constraint g is going to be equals to my say x comma y comma z, which will be equals to x minus y plus z, like that. I'll leave out the 1, I don't need to use it. My h of x comma y comma z, it will be equals to your x squared plus your y squared, like that. Okay, so now when what will happen here is that first of all, you need to determine the normal vectors. So when you determine the normal vector for this one, this is going to be equals to that's going to be equals to I. Okay, you can take it step by step. I don't need to do that. I've done a lot of questions on this, and I believe you understand where this is coming from. We're just differentiating that. So here I'm going to get 2 what? I'm going to 2 in the j. Okay, then I'll get plus what? Plus 3 in the what? In the k. I'm equating 2. So I'm going to say I'm going to differentiate this, but I'm multiplying by what? I'm multiplying by lambda. So differentiate x here, I get the 1. So 1 by lambda, that's lambda in the what? I'll say lambda in the I. Okay, so this one differentiate, you get a negative 1, so that minus what? Minus lambda in the j. Differentiate this one, you get plus what? You get plus 1, 1 plus 1 times lambda, that's what? That's lambda in the what? In the k. Then this part you're going to say plus. Differentiate this part, you're going to get what? You're going to get 2x multiplied by what? Mu. Remember, we are bringing in another coefficient because we have two constraints. That is going to be uh, 2x in the what? 2x in the I. Then you're going to have mu here, 2y in the what? 2y in the j. So now at this point it's just a matter of correcting the like terms for this part. So how is this going to be? When you correct the like terms, you put the i's alone and the j's alone, the k's alone, something like that. You're going to have your lambda here. Okay, your lambda plus mu 2x in the what? In the I. Then I'm going to say plus minus, can I put it like that? Okay, let me say since this one is a positive, I'll say mu 2y minus lambda like that in the j. Then I only have lambda in the k like that on its own. Then here I still have my I plus 2j plus what? 3k. So now we can equate them. So the coefficient for this one is a 1, so it's just 1 is equals to lambda plus mu 2x. Then that the other part will be 2 is equals to mu 2y minus lambda. So the other one is going to be 3 is equals to what? 3 is equals to lambda. Okay, so now we can now determine what our value of x is and what our value of y is. So we know that for this part, I've found out that my lambda is a 3, so I just need to substitute in these two. So I'll say y1 is equals to 3 plus mu 2x. Okay, so if you make x a subject of the formula here, you say your x will be equals to minus 1 over what? Minus 1 over mu. So if you substitute in this equation, you're going to say it is your 2 is equals to mu 2y minus the 3, which is our lambda there. Your y will be equals to 5 over what? 2 mu, like that. So now what is remaining? We need to determine what our z is in that case. Okay, we need to determine what our z is in that case. But before I do that, I would love to determine what the actual value of mu is. Okay, so I'll need to use those values of x and the values of y that I have. So for now, for me to do that, since I don't have a z, I have to use this equation here. So that is like my x squared plus y squared is equals to what? Is equals to 1. So this is going to help me to determine my mu. So if I add the z, even if I replace in this equation, it's still going to be the same value. So you're going to say minus 1 over mu squared plus 5 over 2 mu squared is equals to 1. So when we do some algebra here, okay, what you're going to end up with is that your mu is going to be equals to positive or negative root 29 divided by what? Divided by 2. Okay, you can try to work it out step by step, but that is what you're going to get. If you don't get the same, you can try to communicate to us in the comment section. Okay, so now we know that our x, we said our x was equals to minus 1 over what? minus 1 over mu. Then our y was equals to 5 over what? 2 mu there. Okay, so now I can now determine what my x is and what my y is. So when you do the substitution here, where there is mu replaced with whatever that we have here, so we're going to say this is our x is equals to minus 1 over, our mu is positive or negative, root 29 divided by what? Divided by 2. So you observe that if I multiply this one by that one, I'll get a negative. So meaning I have x is equals to negative. The negative times that negative, I get positive, but that would be like a 2 over what? Root 29. You do the same for the what? For the y. Your y is going to be equals to your y is going to be equals to positive or negative 5 over what? 5 over root 29. Okay, that's going to be root 29 like that. Okay, so that's what we have as a that's what we have as our x and our what? Our x and our y. Okay, so we say our x will be equals to we have said our x is equals to positive or negative or positive to root 29. Okay, then our y we said is equals to what? Our y is equals to positive or negative 5 root 29 like that. So that is going to help us to determine our value of z. So to determine the value of z, we just need to substitute in this equation that we have here, which is one of our constants that has a z. So here we can come and say negative or positive 2 over root 29, then that will be minus positive or negative 5 over root 29, okay, plus z is equals to what? Is equals to 1. So your z is nothing, will be nothing but equals to what? 1 plus or minus 7 over what? Over root 29. You can try to take it step by step. You're going to arrive at that answer. Okay, so now we have our x, we have our y, and we have our z. What else is remaining? So what is remaining now is just to determine the maximum value of that function. And what do? We just substitute in the equation that we have. So you can say our f of x comma y comma z is equals to this function. Where there's x, we put our x value there. Okay, we put our x values. So here you can take it step by step. You can start with negative, start with positive here, a positive, then again you go to what? Positive, negative, negative. But you can as well just put them together. It's simply one and the same thing. So when you substitute there for the x, that will be minus positive, minus or positive divided by square root of 29. That's our x plus that's going to be 2 multiplied by positive or negative 5 over root 29. Okay, root 29 there. Then that will be plus the z, which is going to be, I'll say 3. I'll multiply the 1 by 3 plus then the 7 by 3, that will be 21 divided by root 29. So what you're going to find out is that the value that you're going to have is to be a 3 positive or negative root what? Root 29. So now for us to determine, since we are looking for the max, here we have two values. We have a 3 plus root 29 as well as what? 3 minus root 29. This now happens to be what? Our max, our maximum. Okay, so that's how we go about answering these questions, and that's how we go about applying the LaGrange multipliers to determine the minimas as well as the maximas of a given function. So that's all in this video. Thank you very much for watching.